Alright, so hi everyone, good morning. Thanks for coming. That is really loud. Is this better? Can you guys hear me okay now? I'll clean the slides from here, so alright, let's figure this out. So I'm Anu Kanan. I work for Motorola Solutions, right? So I don't know how many of you are familiar with Motorola. We make rugged handheld mobile computers that's based off on Android. So think of times, say you go to a Walmart or a Target, you see the guys carrying those big, heavy, rugged devices. So that's the kind of stuff we make. Or when a FedEx guy comes to your place and you sign on a little pad, that device is what we make. So our market is very different. Our customers are mostly enterprises, Target, Best Buy, Costco, Walmart, like your entire warehouse, distribution center, the back end stuff. So I was looking at the Droidcon's lineup, right? Mostly everything was app-based, right? Whereas our space, we create our own hardware, we make custom hardware, heavy-duty barcode scanners. So we dabble a lot with hardware and, apps for that and SDKs for that. So I wanted to spend some time here, walking you guys through stuff that we've done and some lessons learned. So think of it more of a knowledge-sharing talk. I'm not an expert in the stuff I'm going to speak on, but it's just stuff that I've learned along the way that I wanted to share. And this stuff is mostly stuff that ODMs and OEMs do. So there's not too much literature out there online. So I just wanted to share some of the things that I've learned along the way. Hoping to keep this a little interactive. So if any of you have any questions, please raise your hand and we can take it then and there, and you don't have to wait till I finish. So how many of you are familiar with what NDK is and have written a JNI app? Oh wow, awesome. Alright, so is that mostly for hardware or software? Software side, quick example? Gaming, absolutely, okay. How many of you use JNI for gaming, whatever, like the game app or something? Right, so what do you use for? Perfect, alright. So I'm not sure you'll have anything new here, but just try and see where we can share and learn, right? So the agenda is like a quick overview of NDK for those who aren't familiar with it, right? How does it play, and walk you through some JNI stuff. Again, you guys are probably familiar with JNI, but nonetheless, just a quick result. And use cases, when is someone likely to use NDK, right? For portability, performance, security, and some aspects of that, and some tips and troubleshooting tips as well. And I can walk you through how we add our custom hardware and expose it to our customers. And just a quick slide on art. So NDK, right? You guys already mentioned it. So he uses it for gaming. He uses it for audio, compression. They want to do FFTs and severe image processing stuff. So use cases are like that are when you would want to use NDK, right? For example, you have the 360 camera out there, where they're like constantly streaming video. So they've created a custom chip, right? Mounted a camera on it, and basically that still leverages stock Android, but you go over and beyond what Android gives you already, right? You can't use, you kind of use the camera HAL and the camera interface, but there's more that you want to do that's custom to you, that's custom to your chipset, right? So NDK gives you the leverage, basically you can use NDK to extend Android and make it custom and add your own software algorithms or add your own custom hardware. And it's not that you're doing something out. This is the recommended way of going about it. It's a sustainable model. So NDK stands for Native Development Kit, for those who aren't familiar with it, right? So some of the use cases would be like abstracting software heavy lifting, like in this case gaming, or in this case audio compression. In my case, we do a lot of image processing algorithms in NDK. or you achieve low-level hardware direction. Say you want to go directly to an I2C driver, or say you want to go directly to, a max type reader. You would leverage NDK for that, right? And the whole beauty of this is it lets you extend the Android platform, customized to your value add that you want to put out there in the market. Right? So it gives you this whole tool set, like a whole experience, if you will. You have support for threading, you have support for memory management, you have chipset support, your x86 or MIPS or what have you. And a lot of people primarily use it, to transport legacy code. Right? You already have all your algorithms written in C. Why would you, rewrite it in Java? And of course, performance. So, okay, what if you're like, okay. Yeah, yep. All right. Okay, hang on a second. And someone called. No, I think it's frozen. All right. Sorry. Hi. Yeah, I think it's.
It's Windows and it works.
Awesome, thanks. Yeah, so this is just a high-level view of where, the NDK process resides, right? So I got this diagram from the Intel website, so it's not something I drew myself, right? So think of this as a process in which your Dalvik VM also exists as a component of it, and within that you have your native library talking directly to your native class with some dynamic libraries and stuff. So this is kind of a split up of, your app is up there, right? And this is your regular, most apps today just work in this model, right? So with NDK, essentially you have your application up here speaking directly to the machine code, right? So you're bypassing the whole bytecode, Java to machine code, bytecode and bytecode to machine code conversion. So you're going directly to machine code. So what exactly is JNI, right? So JNI is one of the core components of this entire NDK. Think of it as it's a native interface, right? It's a programming layer between Java and your C or C++, and it's not just one way. You can go back and call into Java as well. So this is a spec by Oracle, and I'm sure anyone who's dabbled with JNI has opened that document at some point or the other. That's like your Bible. It's not the best documented manual out there, but it has everything, right? It's all up to you. The more times you read it, the more, you just interpret it differently each time you read it. So it's a great doc. It's not the most verbose, but it has everything you need to get going, right? So this is essentially the layer between your managed Java code, with your garbage collectors, and Java's like pretty managed. I think all of you know that, right? So you use JNI to move from a managed environment to an unmanaged, and get your C code. So it doesn't really integrate with Dalvik. I need to change that a bit. But essentially, it gives you a way to speak between, the two environments, right? I know it's too early to talk about function pointers this morning. I still haven't had my coffee yet. But think of it as you're creating an instance of a Java VM, right? And within that, you get an environment that you can play in and call your methods in, right? So it works in a process. So a given process can have multiple VMs, but Android kind of limits you to one. So you can just have one Java VM. But within that, each thread kind of creates an environment for itself that you can then use and call methods. So, yeah. So just a quick, any questions so far on JNI or NDK? I'm guessing now everyone's still waking up. So moving to performance, right? So where we use it. So in our space, to me, we largely use it for portability and for performance, right? So when I say portability, we have devices running Windows Mobile, Windows CE, as well as Android, right? So we have crazy image processing algorithms that I need working on all three operating systems, right? So I can't port my algorithms each time to a different OS, right? And not just a different OS, you have KitKat, L coming out, Jelly Bean, Gingerbread. So it just gets too unmanageable pretty soon, right? So the way we've architected is like we have some core C or C++ components, right? And that's built using your regular C libraries, and then we have these build scripts on top that then build it for like Android, Linux, Windows, Windows Mobile, what have you. So you can structure your code pretty well, so you can leverage the same algorithm, but build, say a DLL for Windows Mobile or a .so file for Android. So that's primarily where we use it. The other big use is, you get access to low-level hardware directly. So we've added like custom cameras and imagers, right? So a lot of them use I2C, right? So if it was connected via USB, we could have tried leveraging the camera framework, right? But because we go into the hardware directly, we directly call into the I2C drivers and access the hardware. So you get direct access to low-level hardware, with this approach. The other thing is ample support for third-party libraries, right? You have your curl libraries, your SSL libraries. So there's a lot that you could leverage. If you actually look at the Android AOSP build that you get, there are a lot of third-party libraries there that you can actually leverage in your JNI code. So you don't have to reinvent the wheel each time, right? I already spoke about porting software across OSs, right? The other useful thing that I personally found was it's very easy to use, right? In terms of you could build it using Eclipse now, you could build it using just Ant, you could build it using Windows, Ubuntu, what have you, right? So you don't need anything special. Like I have a Windows machine here, but I have an Ubuntu machine at work, right? So on Windows, I just downloaded a zip file, and Android gives you everything you need to get going. It's one zip file that you unzip, and you're good to go, right? The other thing was multi-threading support. I think Kevin spoke about threading in Android yesterday, right? I don't know how many of you attended that, but he stopped at threading at an Android level, right? But the thing is, you can actually start creating multiple threads and call into native, right? So I'm assuming, given the number of hands that were raised, you guys are familiar with loading your own .so files, right? So a good example of what we do is, an analogy would be like, say you want to do face recognition, right? So you have in a picture, you have like 5 people in it, right? So we load the library that does face recognition, right? So we spawn off different threads, that we first identify where the faces are in a different module, spawn off different threads to call into the same library to do face recognition on each face. So that way you're really leveraging, you're going from single to, parallel processing, if you will. So you can actually leverage threading support that's in both Dalvik as well as native, because at the end of the day, it uses the same pthread concept, it's all Linux threads in the background. So the concepts are pretty similar, so long as you're careful about memory and, moving across, it's you can actually architect your code to make it really powerful. System permissions is another thing that you can leverage. So I'm trying to focus on how you can write an Android app that can call into native, right? So a good one of the things we found was you write an app, right? So you have a UI component to it, but you also have a background service that's shipped along with the APK, right? So now because we don't work on a consumer device, so we have the entire stack, right? So you can set permissions on your service to system, right? So that automatically gives you access to a lot of other files and resources and what have you, right? So your native library that you load from your APK automatically inherits permissions from the app, right? So now when the app is a service and not an activity, it becomes that much more powerful because now your entire APK is like it's granted system level permissions, and your service has access to go into the files directly and stuff. So again, you can be creative there, right? Create a background service that so that way, regardless of which app is calling into your app, the tasks that you want to do would have system permissions. So that's really helped us, get a lot. So because we can then gate how we respond to the calling apps, but at the same time, give them the performance for the tasks. Yeah. So some of the tips that we did use the default settings, and then we realized that it doesn't help with performance. So these were some of the tweaks we made. Leverage chipset flags, right? Any chipset that you're targeting to, whether it's your custom hardware or whether you're going to launch only on, say, a Samsung device or a Nexus device, you could look up the chipset architecture document from that chipset and leverage your flags a lot to streamline your performance. Yeah. I absolutely can't hear you.
It makes sense if you're specific
Exactly. So So the question was, how do you scale this across architectures, right? This makes sense if you're targeting a particular architecture. So when you build your native component, right? So the whole point is you're writing directly to machine code, right? So machine code is specific to a chipset, right? So if it's an ARM V7 or just an ARM V5 or MIPS or x86, you have different chipsets. So when you're building your native component, there's actually a make file there called application.make. So there you can actually clearly specify to what chipsets you want to target your build towards. So in our case, we only focus, a particular chipset. So we go ahead and tweak the performance for that particular chipset. But if you're writing a software algorithm, leverage that. And within your code, you can actually add like if-else, if-def tags to say if ARM leverage these flags, or if x86, you can leverage Neon or whatever Intel provides. So the other thing was we used we didn't just rely on native to do a lot of things, right? Certain places we actually relied on Java from native to do certain things, right? So one good example was for security or stuff, right? But the thing is with native again, you still want to rely on certain libraries that Java provides because it's more standard, right? So with JNI, you could cache you could find a class that's running in Java and cache those IDs of the classes, of the methods, of the different member variables and call back into Java. So say you have your own custom class, right? So from your native code, you can call back into your custom class and say, that the stuff that was implemented there, give me the result. So you could work both ways and leverage Java code as well as native code. How many of you are familiar with get array region and get array elements? Okay, I'm gonna let that go. So we have use cases where we get a buffer. We leverage the camera framework, right? Get a buffer of an image, and this is coming at 30 frames per second, 60 frames per second, what have you, right? And you're processing every single frame. So, and that frame processing, because it's so time consuming and resource intensive, we do that in native code, right? So we are sending frames to the native code at 30 frames per second, which is pretty high, right? And everything from Java to native is a local reference, which means it's actually copied. Okay, so when you copy data, think of it as 30, like a 2 meg or a 3 meg buffer copy each, 30 times a second. That's pretty intense. So what you could alternatively do is, instead of getting the entire region, right, you could swap it with this call called get array elements and specify I do want, say you have, for your sake of simplicity, think of it as a 1D array with 1,000 elements, right? You're not going to process all 1,000 in your algorithm. You just want 20 to 30, right? Those elements from index 20 to 30. So you could say get array elements starting from 20, ending at 30 into main. So when you copy it over, you copy just the subset that you want to work on, right? And the other thing is, when you release that array, right, you have three options called JNI, commit, abort, and default. So by default, people just use default, right? So what's really happening is, when you copy it from Java to native, right, it actually makes a copy in the native. So when you release it with default, it updates the copy back in Java, which is really unnecessary, especially if you're not if your algorithm's completely in native, you have no business copying it back into Java and just wasting time there, right? So changing it to abort would be more useful, because then your array in native remains, but your array in Java is just garbage collector. So this again helped us in terms of performance, because you're not doing a array copy each time unnecessarily. The other things were exceptions, right? So exceptions can get very tricky because you can't debug. You don't know where the exceptions occurred, right? So you can use this check. You can check. So that was an issue where my code was crashing in Java, right? So Java was calling into native, right? And I was calling a callback back into Java, but something in Java was throwing an exception, and things would just crash because it wouldn't proceed in the native layer or proceed in the Java code. So you could add this check after every callback that you call back into Java, just to ensure that things are working well. Right? C++ does not, there are no exception support for that, so this is primarily for C, right? And I think all the guys who raised their hands would agree with me that debugging this is a nightmare, right? So it's an absolute nightmare. So one of the things that you could try is setting this, you can do ADB shell set properties, check JNI, and then run your app. So any leaks or any mismatches in your code gets printed out. So when your app crashes, say you've called the JNI method, the parameters have to match, right? So you're basically mapping your Java data types to your native data types, right? And that's what JNI specifies, that mapping, right? So if you've screwed up somewhere with that mapping, check JNI really helps. So there are a bunch of things that check JNI helps you with, that you could just try it out to ensure the quality of your app. Any questions? Yeah. I've used byte buffers, but I haven't used those direct byte buffers. I can't wrap my head around that. I tried my best to figure out how it works, but I haven't had much time. Because the other thing is, we work with image formats, right? So I need like an NV21 or like an RGB. So I have very specific image formats. So if they're not, you can't pack them into proper bytes, it gets a little messy. So I'm not too sure how those direct byte buffers work. It just didn't work for an NV21 image. Sorry, the question was, have you worked with direct byte buffers? And the answer was, sorry. Any other questions? Or? Yes. All right. So we're still here. So basically, the point I was trying to make here was there are twofold advantages to NDK. One is portability, right? In terms of OSs, in terms of hardware, and the other is performance. And the performance, you could tweak it to your chipset that you're targeting. So moving forward, this is regarding security. So native code is not impregnable, right? It's still vulnerable, but it's just that much harder to disassemble, right? So try to move all your code as much as you can into native, right? So there are two ways of looking at security. One is just looking at your code. How much can they do a OBJ dump on your code and what data comes out, right? Or do a redelf on it and see what you get. So that's, wow, okay. If you say so. Alright. So in terms of security, the point is, yeah, so it's that much harder to disassemble. So moving it into native gives you that element of, barrier to entry is slightly raised, right? With Java, you could just look at your classes file and you get all the value add that you've probably included if you've not stripped it properly, right? So with native, it's just slightly more difficult to get to. And with permissions, I think I already mentioned how it just inherits the permissions the calling app is calling. So it's not like you can write a rogue native library that suddenly gets permissions to do whatever it pleases. It's still very much in the sandbox, Android sandbox of the app. Reverse JNI we mentioned. So the access to system files and IO is what I told you. So we have a service that's granted system permissions, so we get directly to our hardware. Right. So these were some of the things that we've learned along the way. Right. So in terms of just coding practices, try and keep things, qualify them with static as much as possible. So when you do an OPJ dump, you'll see that it doesn't go into the read-only section, and it's pretty decently hidden, right? The other thing you could do is you could still call into a lot of the base Android classes from your JNI, right? You could still call into your android.build.os and get your build number or your device name, or you could even call android.activity and get the current activity that's running and get the package name. So a lot of guys recommend that for security. So stuff like this is runtime. So you can't have some third-party app, just call into your native app. So your native code is calling back to see what app is running, and only if it's something you recognize does your algorithm run. So that's another way of protecting your algorithms at runtime. Again, if you have a public key, private key that you want to hash and check, that's again a good way of doing it at runtime, right? The other thing we do is when I say native, it's mostly C code, right? So there's a whole bunch of C files. So the way we build it is build it into a dot. How many of you are familiar with what a .a file is? Just one. Okay, so I'll explain that first, right? So you guys are familiar with DLLs? Yes, no. A lot of you guys are. So with DLLs, you have a static DLL and a dynamic DLL, right? So a static DLL cannot, it doesn't have a life of its own. It has to reside within another DLL, right? So the same concept in Linux. It's a .a file is it's an archive file. It doesn't have a life of its own. So it's basically a collection of object files that is like a static lib, right? That gets built into a shared object, that's a .so file. And a .so file is the one that you would load and call functions into and run with. So you can have multiple .so files that get combined into a .so file. Okay, a .so is a shared object. It's essentially a DLL in Android. So you can't have a .so file inside a .so file. So that's something Android doesn't allow, right? The build script doesn't allow. But you can have multiple .a files in a .so file. Alright, so again, this is something you could use for your obscurity. You can have a .a file built into another .a file. That's perfectly valid, right? And then the combined .a file is something that would go into an SO file. So you can play tricks there. If you guys want build scripts and stuff, I can help you with that. The visibility hidden is another good flag that you can set in your android.make file in the JNI root. right? So this basically hides all your function names from the symbol table. So when you do an OBJ dump, you get the entire symbol table dumped out, right? So this basically hides it from there, but you could still call it because you have the JNI export flag next to it. And again, this JNI export is something you can configure. You can say hidden or default or open. So you could play around there as well. There's one caveat though. I do know that if you use ProGuard in your Java app with native, good luck with that, right? Yeah, it mangles the names in Java, so ProGuard does not apply to native. I wish it did, but it doesn't. ProGuard is very, very Java specific. So if you have native code within your Java app, ProGuard is really not going to help. So you need to do your own additional security mechanisms. Like, you could get a third-party obfuscation tool, right, to obfuscate your native code, or you could do, I don't know, there's some some OBJ tools that you could use to strip out stuff or change things. Any questions so far? Okay. Yeah, so last 10 minutes, I wanted to share some info on how we add custom hardware, right? I don't know if it's applicable to a lot of you, but this is the Android recommended way of extending the Android platform to add your own hardware, right? So Android exposes a bunch of interfaces. You have your camera, you have your printer, you have some basic interfaces, right? But if you want to extend it, add your own hardware, add your own interface to the hardware, this is the model, right? So you have your Android application. Most of us live in this world where we just use the stock Android APIs, right? And this speaks to the HAL here, right? Again, all of that is crossing JNI. So we all live with Java and JNI, but it's just very, very well abstracted, right? So the Java framework calls into the HAL calls into your camera drivers, and the drivers then call into the actual hardware, right? So with what we're trying to do is extending that. So you have a parallel silo, if you will. So we have our own custom hardware framework for it, JNI to it, and that again extends the Android SDK to hit your applications. So this extension is perfectly valid, legal. You're not breaking any Android rules so long as you pass CTS with changes like these, right? But it's a very common way of extending your value adds into the market. So the way you do it is, how many of you build your own hardware here? No? Thinking of building your own hardware? Awesome. All right. So you guys would find this slide, because this stuff, it's not the dark arts, right? It's just that it's not used by a lot of people. So if you go up online and look for it, there's not much help you can get, right? So if you go into this folder path in the Android framework, right? This is your MyDroid Android file system, and you go into device sample. Whatever your Diane Hackbone or whatever, she's written a lot of the stuff, right? So they have a good sample on how to achieve this, right? So you basically extend the device folder. Right now you have common, and then you have like a whole bunch of devices there for Samsung, your Motorola, your Nexus. So you have all the device details here. So you can actually add your own into this folder, and if you look at it, it has apps, etc., framework over there, right? So you would realize that this is a subset of the larger Android build tree, right? So it's pretty beautiful, because anything you put in the overlays folder, when you do a full build, right, you can just set up the makefile here, that when you do an Android build, it actually calls into this makefile, and you're setting your product name and your product details here, right? And any files on the overlays folder gets overlaid onto the actual Android. So it actually goes in your Android base for Java or what have you. So say you want to change the colors template, right? You want to add your own 5 different colors that you want. You could actually throw the colors XML into this file, and when you do a full build, it just gets overlaid into the actual Android colors.xml and gets applied. Ditto with apps, etc. and framework. So apps, you can create your own system apps and throw it in there, and it gets rolled in as part of the build system, right? You could put your permissions into the etc. folder and it'll get rolled in. Framework is where a lot of our meat goes, because the framework is where you have all your actual, your JNI stuff and your .so files. And the SDK add-on is what I wanted to add to Ty Smith's talk yesterday, right? So he spoke about I think that was a beautiful talk. I think I'm just waiting for his slides because the design methodologies he specified there were really good, right? So Android gives you a way to leverage that and add to the SDK with your own stuff. So the idea is you do a full build with your product, build, and then you do another build with the SDK, right? And it creates your SDK add-on.jar files that you can then expose to your end users, that they can then use Eclipse or Maven or whatever and pull those files. So that way you're not going, you're still following the Android way of programming and interfaces, but you just expose your own APIs and plugins. Alright, so again, this stuff is not there anywhere, so this is extremely useful. So when you add your own SDK add-on, you're essentially providing your Java jar files, right? So anyone goes in there, they can see your complete APIs. If you want to strip that to expose just the APIs you want your calling application to use, this stubs.txt file lets you do that. It lets you hide all the other underlying. Get what I'm saying? So say you have an API layer, right, that you want the calling app to call. That API layer is underneath calling 3 different components. Now those 3 different components are private to you. The calling app is never going to call them ever. So you can architect your add-on such that only the public API interface is really exposed and hide everything else. So that functionality is again there with this file. You just have to make use of it. So that way it keeps your SDK size small. So it's more both productivity and security. Right? And wow, just on time. So the other question that's of late been making the news is about the Android runtime. So I haven't tried it out. Complete disclaimer, I haven't played with it much. I just did some digging up on it and researching it. So it turns out that you have your Java's just-in-time compiler, right? So you use Java primarily because to the gentleman who's no longer here, his question was how do you ensure it runs on all. Oh yeah, there you are. So ensure how it runs on all different devices, right? So Java compiles it to a bytecode that would then work on everything. So your Dalvik VM is essentially converting that bytecode to machine code just in time for when it requires to be run. Correct? So what they've done with ART is they've converted everything to machine code when the package is installed. When your APK is installed, everything gets converted to machine code. So there's no runtime, conversion happening. So they found that apps are, the speed of the apps are increasing like tremendously, like 3 to like 5 times, depending on how. Almost in line with how the Apple does. Apple, everything is machine code already because they know the exact chipset architecture, right? So everything is converted to machine code. So for folks who were using NDK primarily for performance reasons, art may not be that useful because you guys are already in the machine code layer, so it's not going to help. But so there were questions on is NDK still relevant? Do you still need to use it? So on and so forth. But I think it still is because of your custom algorithms or custom hardware or portability. It still makes sense. So that was it, and I added a couple of details on if you want to get started and play with this and stuff, there's plenty of literature online to get you started, right? A lot of tutorials on how to write your first JNI program. The JNI, like when you download NDK itself, it gives you a whole bunch of sample apps that you could use to get started, and you could then go on and create your own. There are a couple of Google groups that people are really, forthcoming and helpful. So there's a group on NDK, there's a group on porting, so feel free to post your messages there. And then the other two PDFs were just like some good stuff that I found online that could help you on this journey. So that's it. Thank you.
So you mentioned problems running hard when using native code. Is that just a matter of saying that you should keep class names or method names that your native code is going to be calling, or what are some?
So, question was, how do you manage ProGuard with native code? So, ProGuard basically mangles your method names, right? So, say you're calling into native dot, get string or get result or something. So that if that gets mangled, it's not going to find it at link time. So you want to explicitly say that this is a native call, so do not mangle it. So you just have to structure it such that. Yeah, that should help find it. Anything else? Yeah.
The slide about custom hardware that you're referring to, like a system built, like that would be only
Yeah, so the question was the custom hardware, when would that be useful, right? So that would be useful if, I think most of the guys who would find that useful are in Maker Faire right now, creating your own hardware, but it would be useful for guys like that. So if you're writing an app towards your Samsungs and Nexus phones, probably not, but if you're writing your own custom hardware, like, the camera guys outside, the 360 camera guys, they get the stock Android and then add their own stuff, and everything is embedded and shipped with your product. This would be extremely useful in those use cases because it just becomes so much more sustainable and manageable. Your code, because you're always writing towards an SDK, right? You could have your portfolio grow, so you could have like 3 or 4 devices running similar software, but so long as you keep your SDK layer the same, any apps towards it does not have to be recompiled. So it just lets you manage it in a very, very sustainable format. Anything else? And of course, testing. It really helps with testing as well, because you're testing towards one interface, and it's easier to manage. So I'm on Twitter or email if you guys have any questions. Thank you.